talk about what's called translational equilibrium. For an object to be in translational equilibrium, the following condition has to be true. The sum of all the forces has to be zero. If all the forces add up to zero, what's your acceleration exactly as a number? Okay? We're going to try and dive into that concept a little bit more. So another way of writing this, if all the forces add to zero, that really means the forces up have to equal the forces down, and the forces left have to equal the forces right. That's the method that I would use if I was doing components. Now, we are going to be looking at situations today with angles. Did I say angles? Not components. We're going to try and go one step further and say, can we use what's called the sine law and save ourselves a lot of writing? And the answer is, for these specific situations, we can. Because there's another way to visualize adding to zero. If I'm walking a displacement and I go this far, and then I add tip to tail this far, and then I add tip to tail that far, and I end up back where I started from, what's my displacement? If those are three force vectors, what do those forces add up to? Same answer. If you know that you're not accelerating, if you know that the net force on you is zero, if you have three forces, and that's what we're going to be primarily looking at, it means you can add them together, tip to tail, tip to tail, tip to tail, and if you end up with the final vector back where you started from, that has to be a zero. So another way to think about it is force 1 plus force 2 plus force 3. If those are three vector forces, those have to add to zero. Why? Because much like a displacement, I ended up back where I started from. That is a situation in translational equilibrium. Example 1 says, find the tension in both cables. I'm going to call cable 1 T1. I'm going to call cable 2 T2. Or if they don't label them, sometimes I'll call them TL for left and TR for right, but I will label them. They want me to find the tension in both cables. You could do this with components. We're going to choose not to. Instead, we're going to say this is a good job for a free body diagram. Although, Suhani, did they give me a picture? I'm going to label the picture. Where I'm going to label is the node where all three ropes connect. All three forces connect. What are the forces acting on this, Suhani? Get the obvious one. Definitely going to have mg down. And then it looks like I have tension 1 and tension 2. Is this situation accelerating? So the net force must be adding up to, which means I can make a vector triangle out of this. How? I have three forces, one straight down, one up at an angle, one horizontal. When you're drawing your vector triangle, always draw the easiest force first. Students have a tendency to want to, don't circle that. Students have a tendency to want to deal with the yuck. You want patience. Draw the easiest force first. Which is the easiest force? The answer should be fairly obvious. Yes, the obvious one. So here's what I'm going to do. I'm going to draw gravity first, draw it a bit off to the right like this. Then I always draw the yuckiest force next. Jericho, what's the yuckiest force? Be fairly obvious here. Okay, I'm going to draw T1, tip to tail. Tell me when to stop drawing T1. Let me make gravity a little more vertical. That's a little sloppy. Tell me when to stop drawing T1. How do I know I have to stop right there? Because the third force that I'm going to add to it is exactly horizontal according to the picture. This angle here is 90 degrees. Because this angle is 90 degrees, you can solve it with SOHCAHTOA, but we're going to zoom one step out and we're going to say we're going to use the sine law because the sine law works for both right angle and non-right angle triangles. But we need to get more angles in our picture. The sine law gradient, you're correct. It's on your formula sheet, but you'll probably end up memorizing it out of laziness. So just have patience here. What I need to do is I need to somehow get an angle in here. Here's what I notice. I notice that tension 1 next to a vertical line, Sebastian, how big is that angle? Tension 1 next to a vertical line, how big is that angle? What does every triangle add to? This you need to know. 180 degrees. You're at a bit of a disadvantage. 2 curriculums ago, students would have done a bunch of geometry, grade 8, 9, 10, 11, and 12, and they would have actually been able to just see where the angles went without any effort. 3 curricula ago, 40% of Math 12 was geometry. It was by far the biggest unit, and kids got pretty good at it. You folks have done virtually nothing. A tiny bit of trig, and that's it. And so we're going to have to hopscotch our way around, but I'll show you tricks that we can get there. First of all, if that's 35, if that's 90, how big? Use your calculator or do it in your head, but I would encourage you to use your calculator on a quiz or a test because the number of times I've forgotten to carry the one astonishes me. In this case, it is 55 degrees. Put your pencils down, look up. The sine law says this. If you have any triangle at all, the sine of this angle divided by that has to equal the sine of this angle divided by that, has to equal the sine of this angle divided by that. It's often written as sine of big A over little a equals the sine of big B over little b. It's traditional to use a capital letter for an angle and a lowercase letter for a side. Equals the sine of big C over little c, but we never use 3 at a time. We only use 2 at a time. What I want you to notice is what we're really saying is the angle and the one across from it. The angle and the one across from it. The angle and the one across from it. That's your pair. That's the sine law. It is on the back page of your formula sheet as well. So here, well, Philip, what do you want to find first? Tension 1 or tension 2? I don't care, pick. Tension 1, what's the one that I know? I know mg, so I'm going to use this pair. I'm going to start out by writing the sine of 55 divided by what's across from it, mg, has to equal, and now I'm going to pair this pair, the sine of 90 over tension 1. That's my equation. Where is the T1 right now? On the... Bleh. I guess I'm going to have to multiply tension 1 to the top. I guess I'm going to multiply mg to the top. And I guess I'm going to divide by sine 55. I'll get tension 1 equals mg sine 90 divided by sine 55. I think I can go to my calculator. M is 10. Yeah, I got it all in my picture here. So it's going to be 10 times 9.8. Yeah, I'm doing the whole thing. Sine 90 divided by sine 55. What'd you get? 119.6. I'd probably round that off to 120. Braden, is that okay? Oh, make sure you're in degrees. Sine of 30 should be 0.5. Jericho, what's the next one we need to find? I'm still going to use gravity because you could use your new answer, but why? I'm going to say, okay, I guess the sine of 55 divided by mg, what's across from it, equals, which angle is across from T2? Sine of 35 over T2. Jericho, where is the T2 right now? On the, there. We're going to do the same dealio. We're going to multiply it to the top, divide the sign 55. Mr. Dueck, yes, Jericho. I notice it's exactly the same as T1, but instead of a sign 90, I have a sign 35. Mr. Dueck, yes, Jericho. Can I cleverly just backspace on my calculator and edit and change the 90 to a 35 and save myself some typing? And I get 68.6. That's really the gist of this whole lesson, but we're just going to go to weirder examples and trickier to find angles. I don't like example 1 because one of the lines is horizontal. Braden, I think it's a little too easy. Sorry. Example 2 says find the tension in each rope if M1 is 12.6 kilograms and theta is 34 degrees. So I guess that means that that's 34 degrees and that's 34 degrees. Braden, what are the forces acting on this? Get the obvious one. And then I'm going to call this, how about tension L for left, tension R for right? You could call it tension 1, tension 2, I don't care. What's the angle that tension on the left is making with the roof? How many degrees? What's the angle right here? What's the angle right here? Are the angles the same? I think the tensions are going to be the same. When won't they be the same? Something like example 4, and I will say I like example 4. That's what you're going to see, but we'll get there when we get there. Let's jump back to here. We're still learning to walk before we run. This is a job for a free body diagram. I've kind of done it by labeling my triangle. So now, Braden, is this sign accelerating? Be obvious. Look at it. Is it accelerating? So that means the forces must add to 0. I can draw a closed vector triangle. I'm going to draw the very first one, the easiest one, which is going to be the MG. Because I drew the MG a little bit off to the left, I think I'm going to go this way, then this way. If I had drawn the MG here, I would have gone this way, then this way. There's plenty of room to draw these, but I just, by how I drew it, I'm going to say, okay, there's going to be that tension, which I called tension right, and that tension, which I called tension left. And I know they're going to meet each other at the top because that's adding to 0, ending up back where you started from. What's going to be the tricky part here? Yeah, putting in the angles. Okay. Some recommendations. It wouldn't hurt to go like this and like this in your original picture. Draw those 2 vertical lines in. Eventually, you'll reach the point, Tori, where you can just imagine them, but I have to walk you through this because, Braden, how big is this angle right here? Well, what do these 2 add together to form? 90. So it'll be 90 minus 34, leaving what? That's a useful one because, Braden, it seems to me what Tori just said is tension left when it runs into a vertical line makes what kind of an angle? How big? No. Tension left when it runs into a vertical line makes how big an angle? Is this tension left running into a vertical line? This has got to be. Now, because the mass is hanging in the center, because both angles are the same, this is actually going to end up being an isosceles triangle. Another angle is going to be 56, but I'll show you what if you didn't know that. Here's what I would do next. I would zoom in very heavy to this one. Braden, how big is this angle right here? And I notice that's tension right and a horizontal line. I'm going to draw, don't you draw this? I'm going to add some stuff to my vector triangle. you're going to imagine it. Come on. Don't draw that. How big is that angle? You looked away right when I drew the line. I need you to keep looking up. How big is that angle? Look at the picture above. Is that not tension right hitting a horizontal line? What does tension right form with a horizontal line? How big is this angle? Say it. How big is this angle? How big must this angle be? 180 minus 90 minus 34, which I told you was going to be the case, but we've just proved it. That trick of extending one of your lines horizontal in the triangle, hitting across at 90, and then figuring out what the bottom usually is, what it's going to be angle is, will also work as well. Oh, ah! How big? 68? We've done what I feel is the really hard work. Now it's going to be the sine law. Here is the pair that I know. It's going to be sine of 68 over mg in each of my equations. Let me zoom out a little bit now so I can write. What do you want to find first, Braden? Left? You know what? Let's go like this. Let's do the left on the left. Let's do the right on the right, because that might prevent silly errors. Actually, we'll prove that they're the same. So it's going to be sine of 68 over mg equals, and we're finding tension left. Braden, it would be this pair, so it's going to be sine of this angle, 56, over tension left. Braden, where is the tension left right now? On the, more specific, on the, yeah. Wait. Stop. Look up. Braden, where was tension 2 when we set it up? On the right and on the bottom. Yes? And where was tension 1 when we set it up? On the right and on the bottom. If you want a real shortcut, if you have A over B equals C over D, which is what you're going to always have with the sine law, let's suppose you're trying to get that by itself. Diagonal divides, these multiply. It's going to be A times D divided by C. Let's suppose you want to get the A by itself. Diagonal divides, these, it's going to be B times C divided by D. What if I wanted to get the D by itself? It's going to be B times C divided by A. What if I wanted to get the C by itself? Those multiply, the diagonal one divides. How could I remember that the diagonal one divides? I got nothing. You'll have to come up with something on your own. That works when you have four things. One thing over one thing equals one thing over one thing. That's really cross-multiplying with a vengeance. That's how I do all of these. Philip, if you want to use that shortcut, you can. Otherwise, I've given you the skills to say, where is it right now? On the bottom, and multiply it over. But I'm telling you, you know what we're going to get? It's going to be multiply those, divide by that one. Tension left is going to be mg sine 56 divided by sine 58. I've scrolled down, Braden. What was m? So it's going to be 12.6 times 9.8 times the sine of 56, close bracket, divided by the sine of 58. Did I write down the numbers? Is it 68? Thank you. That makes more sense to me. I was going, wait a minute, those numbers don't look good. What'd you get? I agree. I would probably write 110 newtons. You'll get the same thing for the right-hand tension because you're going to get sine of 68 over mg equals the sine of 56 over tension right. I don't really like that question either because you're really only finding one tension and then you're done. So what am I probably going to give you? Not this. Are there ropes in this question with tensions? Be stupid obvious. Are there ropes in this question with tensions? No. I'm not going to use tip to tail, tip to tail, tip to tail. I call this a beam question because that bridge looks like a beam. Here, I'm going to say everything up has to equal everything down and everything left has to equal everything right. Look at the picture. Do you see anything pointing to the left? Do you see anything pointing to the right? But do you see up and down? Here's our equation. F up has to equal F down. Caden, what forces are pointing up? More specific for FA. Has to equal what forces are pointing down? More specific. Pointing down. FA is not pointing down. Pointing down. Two numbers. Read them to me. Yep. Everything up has to equal everything down. If that wasn't the case, this would have to be accelerating. Is the bridge accelerating? Hopefully not. Get FB by itself. What do you get? $46.60. So for cables, because they're at angles, could do components, I'm going to use the sine law. For beams, because everything is typically going to be at right angles, I'll use everything left equals everything right if there is anything, and I'll use everything up equals everything down. Here's the kind of cable question that I like. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. I'm going to call this one on the left here tension L for left. I'm going to call this one tension R for right. Are the angles the same? Which tension do you think is going to be bigger, left or right? Left is bigger? Right is bigger? Let's find out. This is not that intuitive. I can make an argument either way. Well, we're going to do a free body diagram here on the node. What are the forces acting on? Well, we got tension, we got tension, we got the obvious one. mg. I used 12.6 as a mass twice in a row. I guess I did. I was cutting and pasting. Okay. And it says this is 44 degrees. And it says alpha is 16 degrees. Okay. Is this system accelerating, Tori? That means the net force has to add to what? Which means I'm going to draw a closed vector triangle that comes back to where it starts from. I'm going to do the easiest one first. What's pretty clearly the easiest one? Yeah. Yeah. So I've got more room over here. So I'm going to go, I'll change colors, Mr. Dueck. And I would encourage you, draw a decent sized vector triangle. It makes it easy. MG. And then I guess, Tori, that's the right-hand tension, and a little bit steeper, that's the left-hand tension. My scale might not be quite accurate, but I'm close. All righty. Well, Mr. Dueck said, when in doubt, do that. Tori, how big is this angle right here? How'd you figure that out? 90 minus 44 is what you did? Yes? As opposed to reverse adding the answer to not get the right? Yeah, okay. So I see that tension L forms 46 degrees with a vertical line. Is this tension L hitting a vertical line? Then this is 46 degrees. I got one of them. This other one, I'm going to have to use that trick of shooting out straight across. Alpha with a horizontal line is 16 degrees. So if I shoot straight across, I'll erase this after. How big is this angle right here? 90. How big is this angle right here? 16. This is the one that I want. Is that okay? It's going to be 180 minus 16 minus 90, or just 90 minus 16. Yeah, this is going to be 74 degrees. And now I'm going to get rid of this line, and I'm good to go. I can find the third one. What's the third angle? Well, every triangle adds to 180, so 180 minus minus. Really? Ends in a zero? That's a fluke. Okay. The tricky part is going to be fitting in the angles. From here, it's going to be the sine law. Tori, what do you want to find first? Left tension or right tension? I don't care, pick. Tension left. So we're going to always use this pair, 60 over mg, and we're going to use this pair, sine 74 over TL. Okay, and just so to help me stay organized, Tori, I'm going to do tension left on the left, and then I'll do tension right on the right. So it's going to be sine of 60 over mg equals sine of 74 over. So you can either use formula manipulation, where is the tension L right now on the, times it to the top, divide everything over, or you can realize it's going to be mg sine 74 divided by sine 60. M was 12.6 again, is that right? That was lazy of me. $137, almost even? Yeah. Lather, rinse, repeat. We're going to do the same thing, but we're going to have to tweak things a bit. It's still going to be sine of 60 over mg, but now it's going to be the sine of 46. That's the one that goes with tension right. Tension right is going to be mg sine 46 divided by sine 60. Hey, Mr. Dueck, I can just backspace and edit. Yes, you can. I don't know, I haven't done it yet, but I like your enthusiasms. Oh, that's wrong. 46 bracket. You said 102.5, 103, is that what you said? Which tension was bigger? Left or right? Huh. Here's an application. It says, what's the minimum coefficient of friction? Hey, it's asking us what's mu. I don't know what's mu with you. Required for the 12.3 kilogram mass to hold this system in equilibrium. Ooh. How many masses are there? M1, M2. Let's do our free body diagram on M2. What are the forces acting on it, Graydon? Get the obvious one. How many ropes are there? I think two, yeah? So I'll call this one tension 1. I'll call this one tension 2, or you can call it left and right. What else did you say? What was the last one you said? Friction? Which way? In fact, if this isn't sliding, I think I can say this. Friction is equal to tension 2. That's the only way that can be at rest. Yes, I'm getting there. I haven't drawn a free body diagram over on the left side yet. Let's stick it in since you brought it up, sure. But right now, I'm just looking here because they want me to find the coefficient of friction. I don't even have a coefficient of friction yet. Or, why? Friction is what times what? Oh, so I can say mu times the normal force equals tension 2. I don't know the normal force. Which m? So it's going to be mu m2g now I need to find an expression for tension 2, and then I'll divide by m2g to get the mu by itself. I could divide the m2g now, but I want to leave tension 2 a little clean, so when I plug something in, it's a bit easier, I think. So how am I going to figure out tension 2? Well, now I'm going to look at my free body diagram for right there. What are the forces acting on it? M1g, tension 2, tension 1. Is it accelerating? Nope. So that means I can draw a vector triangle. I'm going to draw the first easiest one first, which is going to be M, go a little higher, Mr. Dueck, M1G. I'll draw the yuckiest one next. I'm pretty sure that's tension 1. Which way am I going to draw tension 1? Up, 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 and I'll stop right there. That's tension 1. Tension 2 is dead horizontal. I need an angle. Well, I notice tension 1, when it hits a vertical line, forms 42 degrees. You know where that is? I think that's right here. I think this is 42 degrees. How big is this angle? How big is this angle? Got to be 90. So now I've got this angle here, 42 degrees. I'm good to go with the sine law. It looks like the sine of 48 over m1g equals the sine of 42 over tension 2. Now I have a choice. I can get this tension 2 by itself and stick it in for here, or because tension 2 is mu m2g, I could replace tension 2 with mu m2g. Those will get you the same place no matter what. I think I'm going to get tension 2 by itself. So I'm going to rewrite this as tension 2 equals m1g sine 42 divided by sine 48. And that's going to go there. I get mu m2g equals m1g sine 48, Mr. Dueck, 42, divided by sine 48. Sebastian, what am I trying to find? How would I get the mu by itself? In fact, something a little bit weird happens. What do you notice? What cancels? This is unusual. It's happened once or twice with us before, but yeah, let me make that a little better. Gravity cancels. What this means is you could put this on any planet and it would still remain in equilibrium. Doesn't depend on the 9.8. So mu is going to be M1, I've scrolled down. What was M1? Sine 42 divided by M2. What's M2? Sine 48. What do you get? Sorry? 0.212, I think, is incorrect. Or am I wrong? I think 0.384 is what my last class got. I see a nod, I see a nod, I see a nod. Units. Yeah, weirdly, it's ratio, no units. That's a pretty tough question. Example 6, one more. Wow, I got the yawns. Made Tori yawn too. Okay. Manat, are the angles different? Will the tensions be the same then? You know what this is a good job for? Did they give me a picture? I'm going to label the picture. So I'm going to have, oh, you know what? I can even tell you mg is 625. That's nice. They gave me the weight, not the mass. Tension 1, tension 2. Normally I use left and right, but since they used rope 1 and rope 2, I'll use their notation so I don't forget partway through and make a mistake. Is this accelerating? That means the sum of all forces has to equal what? Okay. Let's see. I'm going to draw M2. Well, I'm going to draw 625 first. What do you want to find next then? Tension 1 or tension 2? I don't care. Pick. Okay. So it's going to look like this. 625. There's tension 1. There's tension 2. Let's see what angle we can figure out. If you haven't noticed yet, the spoiler is usually the top one we can figure out by looking at this top one here. So this is 49 degrees. If I add in a vertical line, what does tension 2 make with a vertical line? How'd you figure that out? Thank you. I thought you were going to say, oh, I went 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus, until I got the right answer. And oh, it technically works, but there's shorter ways to get there. Yeah, 41 degrees. How does that help? Apparently, rope 2, when it hits a vertical line, forms a 41-degree angle. Rope 2 is hitting a vertical line. I think that forms a 41-degree angle. Okay, I need one more angle. Here's where I'm going to use that line across the page trick. How big is this angle right here? 25 degrees. If I go across, that's 25. That's 90. How big will the bottom right corner be? How'd you figure that out? Okay. So it's going to be 65 degrees. We have two tensions. Which one do you want to find first, Manat? I don't care, pick. So here's my crack in the armor. Oh, I need one more angle. I need to go 90 minus 65, sorry, 180 minus 65 minus 21. What's my mystery angle? Is that right? Yeah. So it's going to be sine of 74 divided by, this was nice, instead of giving us mg, they just said, look, it equals 625. I'll take that. That has to equal, what do you say you want to find first, T1? Okay, that's going to be this pair right here. So it's going to be sine of 41 all over tension 1. Tension 1 is equal to 625 sine 41 divided by sine of 74. What'd you get? Anybody else? 427? See one nod? I got 2 nods. And that's the force newtons. Are we done? No, that's tension 1. Let's find tension 2. We're going to start off with the same sine value, sine of 74 over 625 equals the sine of, okay, what goes with tension 2? 65 over tension 2. I guess it's going to be 625 sine 65 divided by sine 74. Yes? No? Yeah? 589, anybody else? Check here, see what I got for a value. 589? Okay. 589. Looks like a 3. What's your homework? On my computer. Oh, it's the wrong one, should he? Number 1. Number 1, you only need to find one of the chords because both angles are the same. 2 is interesting. Here they're asking you to find MG. I kind of have done it in my head, I think. I don't think you'll need to add both of the 2700 and the 2600. I think one will get you there as long as you have the angles right. I think I already said number 1. 3 is good. You can skip number 4. Skip number 5. Skip number 6. Sorry, do number 6. I said what I said. Do number 6. Do number 7. Do number 8. Do number 9. Number 9 is tough. It's weird because the chord is going downwards towards the wall. It took me a while to figure that one out. So if you find that one tough, you're normal. Number 10 is good. Number 11 is good. Put your pencils down, look up. Oh, there's a 12. I'm sorry. Yeah, 12 is good. So is 12.